All right, if everybody take a seat, I'd like, before we start our last panel, actually we have a one more special thing to do, and I'd like to introduce Jim Green for that.
Okay. Great, thank you very much, Bill. Well, you know, it's my really great pleasure to present our last Planetary Science Division Award. And this is an incredibly important individual in the history of planetary science. From 1971 to 1978, he basically had my position. And I have to tell you, his career is really enviable. I know what he went through. He's written a fabulous book, which is back on the display. Please leaf through that. In fact, when I, 6 years ago, had the opportunity to be the Planetary Science Division Director, I found out about the book and I read it thoroughly. And in fact, what's really great about that is how the rivalries between the scientists, how he's worked with the projects, with the federal budgets, how he helped reshape the missions, and how he met the challenging priorities and schedules and vehicle configurations. And I know what that's all about, and a number of people in the audience do too. But let me tell you his record. 1971, Mariner 9 was launched. 1972, Pioneer 10 was launched. 1973, Mariner 10 was launched. 1975, Viking 1 and 2. 1976, Helios 2 was launched. 1977, Voyager 1 and 2. 1978, Pioneer Venus 1 and 2. Now, if that's not a golden age of planetary science, I don't know what is. And so it's my very great pleasure to give a Planetary Science Appreciation Award to Robert S. Kramer. Well, come on up here. Oh, let me come down. Robert, thank you so very much. Well, you did it.
And now on to our last panel. Andy?
Okay, thank you, Bill. And let me, I know this is not near the end yet, we will be there, but I want to say before I forget to thank Bill and Roger and everybody who put this conference together. It's been terrific. I just want to say, glad you did it. We're going to do things a little differently on this panel than we've done up to now, partly to keep you guys awake. Partly to keep us awake. But what we'd like to do is we're going to have presentations that'll be a little briefer. Each panelist is going to talk for 10 minutes or so. And then we're going to sit down and have a little bit of a roundtable discussion. And I think we had a really nice transition to this in the questions that followed the previous panel, where people were asking about what have we learned from all that we've been through, and how can we use it to improve our chances of succeeding now and in the future. So we're going to be looking back, but we're also going to be looking ahead. And before we get into the discussions, or the presentations, I just want to mention something that David Grinspoon alerted me to several months ago when we were talking about this upcoming anniversary. You know, December marks the 50th anniversary of the very first planetary encounter by Mariner 2. And on December 14th, Mariner 2 flew past Venus at a distance of about 20-something thousand miles, and, there had been a lot of speculation about what Venus might be like. Of course, it was hidden and is hidden by dense, opaque clouds, and so nobody really knew. We had clues to what Venus was like. There were, for example, very strong microwave radiation that had been detected from Earth-based observations, and people speculated that maybe this was due to the fact that Venus was surrounded by a very warm and wet atmosphere. In fact, I remember when I was 5, 6 years old, right at the time of Mariner 2, in my astronomy picture books, there were some paintings that artists had done that showed Venus as a kind of a Jurassic swamp with Venusian dinosaurs. And that looked pretty cool to me. But Mariner 2 made one observation, and it's so elegant. It really is a beautiful example of what can be done with a very little amount of data. It scanned across the disk of Venus with a microwave radiometer, and it looked at how that intensity of microwave emission varied across the disk of the planet. And if they knew that if there was an increase in the intensity towards the center of the disk, then the heat was coming from the surface, whereas if the emission was most intense at the edges, where you're looking through the most atmosphere, then that would point to a very hot atmosphere. Well, guess what? The intensity was greatest in the middle, and that's how we got our first awareness that Venus is in fact a hellishly hot surface underneath an atmosphere that's much less hot. And that simple measurement began the age of in situ planetary exploration. Well, our first speaker is going to talk a little bit about the precursor missions that were so prominent in the early history of the space program. Glenn Bugos is a historian at the NASA Ames Research Center, and in fact, he's written a history of the center called Atmosphere of Freedom, which has come out in 2 editions, and he's written many articles on various topics to do with the history of Ames. He also has an interest in business history and has been a corporate history consultant. So Glenn, have at it, but 10 minutes.
Thanks. So I am a historian, and one issue that confronted me when I joined NASA about a decade ago was how to make sense of LADEE. LADEE started as a robotic precursor, first as a lander for an environmental survey network, then one quick spacecraft to baseline lofted dust before the rush of expected human exploration on the moon. Now LADEE is seen primarily as a science mission, gathering data about the lunar exosphere, while the modular bus is a key part of a private effort to build a lunar network. None of this yet has launched. The technology has changed modestly. How it's been viewed over time has changed dramatically. That's why I first started to look at what it means to be a precursor, and my research is focused largely on the robotic precursors to Apollo. Now, I think it's great that so many of the people at this conference come from JPL. I think if the papers reflected the totality of our agency's solar system exploration, there might be a little bit less about high-resolution photographs and more about data archives, less about rocks and more about atmospheres, less about geomorphology and more about astrobiology and astrochemistry, less about flagships and more about instruments, less about planetary science and more about precursors. Precursors, it's such a hopeful word when applied to a science mission, to a space mission. It suggests that any mission is a forerunner of a logical course of missions to come. Finding logic anywhere makes us hopeful. Today, the word precursor most often means robotic missions to pave the way for human travel by reducing uncertainty. To talk of precursors is to talk, hopefully, of planetary exploration as if space settlement was to come. Precursors can help here, hopefully, at this conference, where historians in science and engineers are coming together to find some common dialogue. I find even that when talking to people in the hallways here, that even how to frame the issue of science and human exploration together, we all have dramatically different expectations of how to do that. The word precursor illuminates contest, conceptual contest, between robotic and human exploration, between practices of manufacturing certainty, between ways of viewing historical progress by looking back to the past, as historians do, or by looking forward to the future, as space architects do, between science and technology, perhaps, depending on how NASA proceeds these next few years, between public and private. My point is, I hope we all use this term with a little bit more sophistication. Today, any PowerPoint of space architecture starts with the Precursor, small, cheap robotic spacecraft, usually in the lower left-hand corner, stepping stones or checkboxes to the ultimate destination in the upper right. If all interested parties can agree that a Precursor addresses a specific knowledge gap in spacecraft technology or in what we will find at our destination, then we all agree that we can use it to declare success or failure, well enough to move forward with a larger, more expensive program. That's one way that the word Precursor invites contest in the negotiation over what data manufactures certainty. Another way the term Precursor invites contest is in whether it is best used by historians or by planners. The hubris of calling anything a precursor ahead of time implies that you can anticipate in the nearest future what missions will actually fly. It is easier to define a mission as a precursor historically, retroactively, once we know how the future unfolds, than it is to define one prescriptively as part of a plan. Yet just because historians can't apply the word precursor with more satisfaction doesn't mean that planners can't use it for their own means. The word precursor has recently undergone rapid change. With the power of Google Books and the NASA STI database, in the decade of the 1960s, I saw only one use of the word precursor applied to space with the Apollo missions. Notably, it was by a chemist in a discipline where the word has an established meaning, as an ingredient that undergoes chemical reaction or metabolic pathway to become a more definitive or stable compound. In the 1970s and 1980s, precursor was used in a dozen, then 100 more different contexts, in situations like Pioneers 10 and 11 being precursors to the more complex Voyager missions. Then in the 1990s, the term exploded into its common meaning. In 1989, notably on the 20th anniversary of the Apollo 11 landing, the first Bush administration announced the Space Exploration Initiative, building out station, a permanent presence on the moon as a precursor to humans on Mars, all preceded by robotic missions. This is when what we came to know as the precursors to Apollo were the robotic precursors, the Ranger impactors, the lunar orbiters, and the Surveyor landers. The history of the early lunar robots is often misinterpreted because of the sheer mass of Apollo in the historiography of the exploration of the moon. In the first years of the space race, before Apollo was announced in 1961, these spacecraft were designed for lunar science, and their experiment packages designed to help planetary scientists understand the geology of the moon. There were 13 successful American encounters with the moon prior to the Apollo landing, the first of which happened less than 5 years before. Quickly and efficiently, these robotic missions laid an experimental foundation for the discipline of lunar science. On the eve of Apollo 11, it was clear which questions remained that the sample return could possibly answer. So these were science missions, but they did, in fact, serve as precursors. With the start of work on the Apollo lander, the robots were repurposed to collect data useful to Apollo engineers. The changes to the robots were generally slight. Removing the cameras on the Rangers was the biggest. The other would be an equatorial focus with the maps and the strain gauge added to the landing pads. Before these robots launched, Apollo designers had declared a nominal definition of the surface of the moon, the bearing strength of the regolith, the protrusion of the boulders. This definition was a little revised with the data that the robots returned. Still, the robots validated that NASA could get to the moon, orbit it, and land on it. At the time, in the 1960s, what was seen as the real precursors, though not by that term, were the human missions, Gemini and the early Apollo flights. Those missions didn't get the attention just because of the astronauts. They were validating the technology that was really on the critical path to Apollo: 2-week trips, EVAs, docking, lunar rendezvous. Looking forward in time from the 1960s, those manned missions were the ones that manufactured certainty about Apollo. Looking backwards from the early 1990s, the robots bear the weight of Apollo history and are now usually cast as precursors. Still, some precursors actually follow a recognizable trajectory that makes sensible narrative of space exploration, whether you look backwards or forwards. Probes into lunetary atmospheres, for example, were imagined in the 1960s as ways of learning about the structure of all the many atmospheres in our solar system. The probes had scientific goals, since atmospheres teach us much about the evolution of planets. They also had engineering goals in that we can design better heat shields and forecast weather at landing sites. There have been a dozen probes since the first probe, the PAET, into the atmosphere of Earth in 1971, up through the Huygens and the Medley suite and the heat shield of MSL. And the progression of ever more sophisticated probes returning ever better data is what those in 1971 might expect to see in 2012. Let's jump forward to the most recent era of precursors and a final way in which the word precursor evokes contest between science and technology, between knowing and doing. The 2005 Exploration Systems Architecture Study, predicated on a big launcher constellation, was what Harry Lambright yesterday delightfully called Precursor. Constellation evoked a reconstruction, both historical and in some ways technological, of Apollo, and of old paths not taken after the Apollo missions. But really, it was fueled by two more recent precursors, Clementine and Lunar Prospector, that showed the moon to be wet. NASA's Constellation Office built a robust robotic precursor program with a dozen prospective missions poised to fill knowledge gaps about the moon. This precursor program took flight much later with the Lunar Reconnaissance Orbiter and LCROSS. NASA's Lunar Precursor program, as I understand it, is now largely in hiatus, or at least construed as science. Since 2010, NASA has embarked on a flexible path and will decide where astronauts will go once a launch vehicle is firmly in hand. It could be the moon, Mars, a moon of Mars, or a near-Earth object. With no destination, there's no immediate need for robots to pave a safe way for astronauts. Still, our knowledge of the planets keeps growing. Over the past decade, there have been 10 expeditions to the moon, orbiters and rovers on Mars, and data useful to the taxonomy of NEOs. There's much to make sense of. Historians have spilt much ink over the interplay between science and technology. Those of us in NASA, rather than directly address that interplay, we use a proxy. If something is funded by the something is funded by the Science Mission Directorate, then it is science. If it is funded by the Human Exploration Mission Directorate, then technology. The NASA Lunar Science Institute right now is funded by both. Let me conclude with it. NLSI is a virtual institute founded in 2008. Its goal is to reinvigorate a discipline of planetary science started, as we have heard yesterday, about 1962. As NASA's institute, NLSI teams crunch new planetary data to make it useful to those in NASA planning missions, robotic or crewed. The NASA Astrobiology Institute served much the same role in the 1990s when Dan Golden kept alive a Mars program with vague precursor ambitions. The NAI teams helped then operationalize the mantra of how exactly to follow the water. The Lunar Science Institute is now being reconceived as a NASA Institute of Science and Exploration, its purview broadened to the moons of Mars and asteroids. Someday national policy or private investment may again shift so that we can talk of precursors. We will again use the word hopefully, anticipating a future history in space. As historians and scientists, we may use the word precursor to bring focus to the contest about how this future will unfold. Thank you.
Thank you, Glenn. Our next speaker is Paige Kaminski, and she is Senior Policy Advisor to the Chief Scientist at NASA headquarters and is a PhD candidate in Science and Technology Studies at Virginia Tech. Now, here's an interesting biographical note. She has previously served as a NASA program examiner at the Office of Management and Budget. And I think we're going to be maybe revisiting that part of her career for her perspectives on what's going on right now. She's also been an analyst in the Federal Aviation Administration's Office of the Associate Administrator for Commercial Space Transportation and Policy and Outreach Administrator at the National Space Society, former editor of the American Astronomical Society's Space Times magazine, winner of the 2012 Sakharov Prize for Space History. She has a master's in science, technology, and public policy from GWU and a bachelor's from Cornell in earth and planetary sciences. And she is going to talk about the Faster, Better, Cheaper program at NASA.
Is this the remote I use? Okay, great. All right, we'll see if I still have anything left to talk about now. Okay, well, a role of the historian or sociologist of science and technology is to make sense of why and how throughout time certain paths in technical fields like solar system exploration are pursued by organizations, nations, and societies, while others are not. Most such social scientists will say the resulting choices can't be seen as based solely on rational decision-making, the state of science and technology, or the idea that these enterprises proceed along a linear path of progress. Rather, they will say, decisions in science and technology, and what's perceived as a success or a failure, also have social and political determinants, and we've already heard a lot about that in this conference. As I see it, determining how and why solar system exploration programs embrace particular forms, scales, and destinations requires accounting for both the technical and the social. And conceiving of solar system exploration as a sociotechnical system or network comprised of many interacting actors. As applied to solar system exploration activities performed by NASA, these actors include NASA leadership, planetary scientists and would-be mission developers in NASA, JPL, industry, and other institutions, U.S. political leadership, the mass media, and sometimes others, all of whom have goals, values, and priorities of their own, as well as particular interests in and definitions of success and failure for space and solar system exploration. It also encompasses, and I want to stress, it encompasses non-human elements, particularly spacecraft, as the technological centerpieces of solar system exploration. Conditions such as the state of the economy, scientific knowledge, other NASA programs, national policies, international space programs, as well as cultural preferences, can serve as influences on, if not arguably part of, the elements of the network. NASA's approach to robotic solar system exploration can thus be seen as the product of how the agency attempts to integrate, resolve differences, and harmonize this network of disparate actors and elements. Conversely, we can think of it being the conflict, the cohesion, and the feedback among these elements that shape solar system exploration. And by viewing solar system exploration in this way, and by seeing strategies in the making, so to speak, we can account more broadly for their emergence, and in turn see the social preferences, expectations of success, and value propositions that have existed for NASA and its missions. This idea that solar system exploration strategies are the product of a continuous struggle to stabilize a network of elements is quite evident in, as just one example, NASA's move to and then away from the faster, better, cheaper approach to solar system exploration within several years' time. Beginning in the 1990s, the science, engineering, and management strategy entailed the pursuit of low-cost missions, up to a couple $100 million, with limited scientific objectives, and that could be flown frequently and visit a variety of destinations as part of a broad portfolio of solar system investigations, such that a single lost mission would not signal disaster for the entire program. As espoused by then NASA Administrator Golden, these missions were encouraged to take certain risks, embracing new technologies and new management techniques to reduce the costs and advance solar system exploration in the long run. So how did the faster, better, cheaper idea come about when it did? Dan Golden is often seen as the catalyst for this initiative, but in short, I would say that the incompatibility of various actors' interests with the mission strategy of the previous decade prompted them to adopt a discourse, if you will, that smaller, lower cost missions were possible and necessary for the vitality of robotic solar system exploration. Planetary scientists had discussed the idea of small missions in the past, but these hadn't materialized, as mission opportunities were budget constrained. As we've heard, in the late 1970s and the 1980s, planetary scientists tried to maximize scientific objectives on what few missions they could secure, this and the mission's dependence on the shuttle led to very costly missions, and only 2 being launched in the 1980s. This experience made the community reflect more carefully on the value of small missions. Meanwhile, staff in the George H.W. Bush White House's National Space Council were frustrated with NASA's penchant for expensive space systems. They had seen the Strategic Defense Initiative organization, for example, deploy a space-based ballistic missile system for relatively inexpensive cost and short schedule, and thought that NASA would need to act similarly and commit to lower cost systems to afford the Bush Space Exploration Initiative. To shore up NASA program costs agency-wide, they brought in the new NASA Administrator, Dan Golden, who was an advocate of mitigating cost growth by shrinking the sizes of missions. Also in the early 1990s, multiple Congresses and the Clinton administration committed to reining in federal discretionary spending, including at NASA. Where the agency was concerned, the Clinton administration, who retained Golden as administrator, prioritized securing funding for the International Space Station, but along with Golden and then head of space science, Wes Huntress, wanted to see a vibrant program for space science. Finally, of course, we've heard already much about this, but the 1993 failure of the billion-dollar Mars Observer and the ensuing media criticism only affirmed for NASA, the science community, and political leadership the prudence of a program of small missions that distributed benefits and risks. So in short, no single mission or no single element promoted the move to faster, better, cheaper. It was a convergence of these conditions that spawned NASA not to pursue more flagship missions, nor to eliminate robotic solar system exploration as the Reagan administration had contemplated, but to focus on small missions as a solution that would satisfy these disparate actors. NASA's earliest experiences with its two low-cost mission programs, Discovery and Mars Surveyor, suggested that perhaps the agency had found in Faster, Better, Cheaper a strategy to synchronize and stabilize the solar system exploration network. Under the new regime, 13 new mission starts were obtained to a diverse range of solar system targets. Some of these missions achieved low cost using off-the-shelf hardware, but many did so using new technologies and management techniques as Golden had advocated. Planetary scientists enjoyed newfound creative license and autonomy under the approach, for example, with the Discovery mission being able to propose and manage entire missions as principal investigators. And mission performance led to a steady stream of science data and results that were published in major scientific journals. The arrival of Mars Pathfinder thrilled the media and political leadership and captured the public imagination as the first successful spacecraft on Mars launched in nearly 20 years. Then in 1999, several Faster, Better, Cheaper missions failed. One, an astrophysics mission Wire in March, then in September, the Mars Climate Observer, Mars Climate Orbiter, thank you. Acronyms. And then in December, the Mars Polar Lander with the two Deep Space 2 technology probes it carried. Independent reviews following the Mars failures found that NASA had cut mission costs too much, trying to achieve the two missions for the price of one, and as a result making mistakes that the agency might well have caught with more reviews and tests. But still the reviewers thought that with adjustments, NASA could and should continue to use Faster, Better, Cheaper as a guiding program management technique. But NASA and Dan Golden backed away from Faster, Better, Cheaper in favor of what I would call a cost-conscious conservatism. Mission costs and sizes did not return to the levels of the 1980s, but NASA began to put more money into each mission. And with each mission costing more, reliability became paramount, and every mission became strategic in value. Failure was no longer an option, and NASA became quite conservative about how it designed and managed missions. I think it's easy to say that NASA abandoned Faster, Better, Cheaper because building reliable, low-cost spacecraft proved too difficult. But this would simply be a technical explanation and not a socio-technical one. NASA might have continued only with small solar system missions with modifications, as the independent reviewers had suggested, or invested in a few flagships, or perhaps invested heavily in technologies for long-run advancement, or perhaps put the extra funds into other programs in NASA altogether. But instead, NASA went in the direction it did because of how the spacecraft failures perturbed the network of actors as it threatened the goals and expectations of them. The planetary community, as far back as 1994, had, and prior to that, I would say, but during the era of faster, better, cheaper, had opined that a mix of mission sizes was optimal to serve science. And in 2000, they released a report through the National Research Council stating that the faster, better, cheaper's approach stand on risk and its restrictions on larger missions had compromised scientific objectives and outcomes. The news media, meanwhile, published stories suggesting NASA had acted incompetently, if not with negligence, on the 2 Mars missions. In hearings, members of Congress blasted NASA for the failures, calling them national embarrassments, and saying that U.S. taxpayers expected and deserved better. Although each of these sets of actors had disparate interests in spacecraft, seeing them respectively as necessities for their profession and their livelihood and the pursuit of scientific knowledge, as symbols of technological achievement and national pride, and as major taxpayer investments necessitating public accountability, the 1999 mission failures were anathema to them all. Success in solar system exploration for all of these actors meant the delivery of near-term results by individual missions, not the promise or prospect of advancements in solar system exploration over the long term, by learning from failure as Golden had envisioned. Discourse about failure thus came to prevail over talk about the need for cost-cutting among the network actors, NASA stakeholders. And this criticism, along with criticism during the time about space shuttle safety issues by NASA's advisory committees, the media, and the Congress, provided the impetus for Golden and NASA via Golden to back away from faster, better, cheaper. With federal budgets just having moved into an era of surpluses, the White House, not wanting the solar system program to fail, worked with NASA to increase space science budgets, fund the Discovery missions at higher levels, introduce the New Frontiers line of moderate missions, and redesign the agency's Mars strategy. So in conclusion, this socio-technical analysis of faster, better, cheaper, and examining history in the making more generally, tells us about the complexity and contingency that governs decisions in solar system exploration. It provides an explanatory context for the forms, goals, and destinations of the solar system exploration program, showing just how instrumental each element of the network is or can be in sculpting the programs that materialize at any given time. It also illustrates the challenges of trying to predict and control the solar system exploration enterprise's future. But even as it shows the difficulty of predicting precisely what will work or be in the future, this analytical approach provides insights into social expectations, preferences, and interests shaping solar system exploration, NASA, and the U.S. space program. The socio-technical examination of faster, better, cheaper's emergence and decline in particular shows that we have become quite a demanding bunch, collectively speaking, and the quest for perfection and high expectations held for NASA and spacecraft success means the agency's reputation constantly hangs in the balance. Think of what this cartoon would have looked like if Curiosity hadn't survived the 7 minutes of terror. Perhaps NASA's attempts to communicate ahead of time just how difficult the feat was would have staved off critical news stories and congressional hearings, but maybe not. As long as our standards remain high while the technical challenges and cost of spaceflight remain formidable, debates and policy shifts will almost certainly continue concerning how best to explore the solar system. Thank you.
Okay, thank you, Amy. Next, we have Scott Hubbard, professor in the Department of Aeronautics and Astronautics at Stanford, and the director of the Stanford Center of Excellence for Commercial Space Transportation. He is the former director of NASA Ames, and he's written a book called Exploring Mars, Chronicles from a Decade of Discovery, which tells in longer form the story that he's about to tell about reinventing the Mars program in the wake of the failures that Amy just talked about. Scott?
Thank you very much, Andy. Let me just start off by saying this is a truly excellent conference. I'd like to thank Bill Berry, our sponsor here, Jim Green, and everyone. When you have an interdisciplinary gathering that brings together such disparate knowledge as historians, sociologists, scientists, engineers, recovering executives, you have a new way of looking at things. And so I'm just delighted to be here. I modified the title just a little bit, Exploring Mars, Following the Water, a talk I've given many times, but I've added in the next decade. Sitting next to my longtime friend and colleague, Wes Huntress, I've discovered that we've become part of history, which but I'm not a historian. Yes, living history. But I'm not a historian, and so I'm going to give a little bit of a look ahead as well of where I think that Mars exploration in particular really ought to be headed. As Andy said, much of what I'm going to talk about is drawn from particularly Chapter 12 of the book that I just published. I have been complimented several times during this conference for being the first Mars czar and putting the program back on track after the twin failures in 1999. But of course it wasn't just me. The large cast of players, including Dan Golden and Steve Isakowitz at OMB, Ed Weiler, Firuz Naderi, Jim Garvin, and a cast of many, many others. What we had the extraordinary opportunity to do was to take nearly a clean sheet of paper and completely restructure a decade of missions. And we started off with the science requirements, what we were trying to do there, and understanding Mars as a system, not a single measurement that hoped to find life, but rather understand the past and present climate, understand the water cycles on Mars, and particularly its biological potential. So among all the questions that we asked, the first among equals was, is life there in the past? Could it even be there today? The conditions of habitability of Mars were paramount in our thinking. And we adopted this phrase to explain what we were doing, not only to our colleagues, but particularly to the taxpayers and their representatives. And I found many, many times in that trip between the first floor and the third floor or fifth floor of NASA headquarters, having somebody step in who is a staffer and say, so what is this Mars thing? And you'd say, well, it's about follow the water and it's understanding the past, present life on Mars. You say, oh, that sort of sounds pretty good. So these kinds of things, although they're sometimes derided as sound bites, give you a way of communication to people who are not insiders that tell them succinctly what you're all about. And I think there's value, great value in that. Now, I have added, with emphasis at the bottom, that this decade of Mars missions was not only intended, and in fact I think has, given us an understanding of Mars as a system, it also was fully intended to prepare for the next decade of sample return. And I'm going to just give you, in the interest of time, only one example, and that is the improvement in landing accuracy. You see up here what we were capable of with Viking, Pathfinder, and then when we got into the current decade, Spirit and Opportunity, we've gone from Viking 174 miles by 62 miles is the footprint, the error ellipse that you had to deal with, down in the case of Spirit and Opportunity to better than half that, 93 miles by 12 miles. Phoenix, 62 by 12. Curiosity, down to 12 miles by 4 miles. We would not have even been able to consider at all going to the foot of Mount Sharp and Gale Crater had this deliberate improvement of landing accuracy, the deliberate increase in rover capability been built into the program, and that was not only to be able to sample the diversity of Mars, but to prepare for the next decade of Mars sample return. So where are we today with respect to Mars? This, I think, is essentially the consensus of groups like the Mars Analysis Program Group, MEPAG. We have lots of evidence of ancient liquid water, surface and ground, past geological environments that have preserved this knowledge, understanding much greater detail, variations in habitability. And so in summary, I think we now have the means to prioritize the sites to go and get samples and bring them back. Modern life? Don't know. We're waiting on the methane results with bated breath, which I think will be coming shortly. So, the next decade is shifting from follow the water, which has been extraordinarily successful, to looking, I would argue, for the fingerprints of life. And the way to do that, as recommended by the National Academy of Sciences and the decadal survey that we have talked about many times, is with a Mars sample return. A campaign of 3 missions to land, get the samples, launch those samples to orbit, return them to Earth. And now, why is this the next logical step? Because looking across the full range of things you might do at Mars, and this has been recently re-endorsed by Orlando Figueroa's Mars Program Planning Group, it gives the greatest increase in knowledge that we can have. It is not only an incremental increase, it is rather a giant step function in knowledge, because samples can now be analyzed by not just a few investigators, but hundreds of investigators, not only by one mobile laboratory, but dozens of laboratories, and using equipment that could not possibly be shrunk in any current environment to the size of a shoebox to put on board a rover on Mars. You can follow the pathways of discovery with samples here on Earth, something that in situ is very difficult to do. So I'll make one reference to the Mars Program Planning Group, the study that was just concluded, and they addressed the question of, as was called for in the decadal survey, can you de-scope significantly the Mars rover that was supposed to cost $2.5 billion and begin this process of caching samples? Can you de-scope that and still recover the fundamental science? Their answer, as independently validated, was definitely yes. A bottom line here of about half of what the proposed amount was for the decadal survey. It does this by reusing material from the Mars Science Laboratory and other details here that I won't go into in the interest of time. So, where are we then on the challenges for Mars sample return? The reason I canceled the Mars sample return that was on the books in the year 2000, because we didn't know where to go that made it worth that large expenditure of time and effort. Today, after this deliberate decade of understanding, we are very well prepared to pick the site to get those high-value samples. We have the capabilities to drive to them, to land accurately. The orbital rendezvous and docking has been largely demonstrated by Orbital Express. Planetary protection and the safing of these samples has been studied. The sample return vehicle, the one that we would bring back these samples to Earth with, was demonstrated through Stardust and Genesis. The main remaining technological challenge is with the so-called Mars Ascent Vehicle. That needs some development, but it's basically a sounding rocket, only it has to land on Mars and sit there for a year and then work with 2 nines reliability. But I think it can be done. So the study by Orlando Figueroa demonstrates that a caching rover to begin the sample return campaign can be developed for far less than the cost of a flagship in 2015 dollars, perhaps 1/2 of that. And I think that given the appropriate technology and instrument development, that a credible Mars sample return mission can now be planned. Thank you.
It was great, Scott, and you also came in under time, which is amazing. Finally, Chaz. Chaz Beichman is the Executive Director of NASA's Exoplanet Science Institute at JPL and Caltech. Starting in the mid-'90s, he helped to develop NASA's exoplanet program, including ambitious missions like the Terrestrial Planet Finder. His research includes the study of debris disks around nearby stars, which are possible remnants of the planetary formation process, and the identification of free-floating, few Jupiter-mass brown dwarfs using the WISE, Spitzer, and Keck telescopes. As a member of the NIRCam instrument team of JWST, he is planning imaging and spectroscopic observations of nearby exoplanets. Chaz?
Yeah. Okay, so it's really an honor to be here at the 50th anniversary of the exploration of our own solar system, and I'm going to speak today briefly from the perspective of a historian, which I am not, of the 50th anniversary of the exploration of exoplanets, and the date on my chart is October 26, 2045. So everything I'm going to say now is my version of history as seen from the 50th anniversary of the discovery of the first exoplanet. So in the 1940s through the 1980s, really, we had the first glimmers of exoplanets that kept coming and going. Astrometry was finding in the 40s 10 Jupiter-mass planets orbiting nearby stars, Barnard Star and other ones. They kept coming and going. Eventually, they just went. In 1952, the year of my birth, Otto Struve, an astronomer, laid out the idea that one of the most burning questions in astronomy was the frequency of planet-like bodies in the galaxy which belong to stars other than our sun, and how shall we proceed to find them? And he laid out the techniques that we're using to this day. Imaging, he regarded as quite limited in scope, given the very great contrast ratio between a planet and its nearby star. Radial velocities, he said, that it's not unreasonable that a planet might exist at a distance of a 50th of an AU, causing a radial velocity variation of a fraction of a kilometer per second, could be just detectable. Transits, he said, would be quite observable, about 2/100ths of a magnitude, and this should be ascertained by modern photoelectric techniques. He basically laid out the entire program that would come to pass some 50 years later. Bruce Campbell and Gordon Walker at the Canada-France-Hawaii telescope pioneered the radial velocity technique, claiming to have found 7 stars that show small but statistically significant long-term trends. Companions of 1 to 9 Jupiter masses are inferred. None of those actually survived contact with reality, but they invented the technique that is being used today. Dave Latham and company actually found what we now would regard as the first planet. It was actually, they called it at that point very modestly, a probable brown dwarf. So that was the 40s into the 80s. By 1995, the floodgates began to open, and so I mark as 1995 really the beginning of exoplanet research, which we're celebrating the 50th anniversary of here today, or at least for the duration of my talk. So I call that the Annus Mirabilis, the half-Jupiter mass companion to a nearby star, 51 Peg. That led to the beginning of the Origins program that Wes and others helped to bring to pass, and it led to the first call by a president of the United States for an advanced telescope. The first call for a telescope by a president since John Adams called for the founding of the U.S. Naval Observatory. So he called for a telescope to look for Earth-like planets and habitable environments around other stars. That led to, over many years after that, the radial velocity teams of Marcy and Butler, Mayor and K. Lowe's found more than 500 radial velocity planets, a lot of them using the NASA Keck telescopes, and we went from the few planets in our solar system with periods shown there from a few days up to 30 years to what we have now is a huge plethora of planets. These are just the radial velocity systems in terms of their period and orbital eccentricity. A remarkable diversity of systems that just becomes more remarkable with every passing day. And this, the hot breaking news, of course, in the last week is that we have a hot Earth orbiting the nearby star Alpha Centauri b. Many more to come, I'm sure. So 2005 to 2015 is the decade, really, of transits. The first ground-based transits were found in 2004, and then the Discovery program discussed here earlier led to the selection of Bill Baruchi's long ridiculed and now, of course, widely acclaimed Kepler program, which has found more than 2,000 planetary candidates. Shown here is just one version of those represented in the image. We have now the plot that Torrance alluded to, where you have a mass of the planet, horizontal axis, its radius, and you see Uranus and Neptune up in the upper right, sort of ice giants. All the systems here in Kepler 11, 6 systems orbiting inside the orbit of Mercury with a range of masses and densities. Are they Earth-like, water planets, gaseous systems with some fraction of rock and hydrogen and helium, all the way down to Earth-like systems, Corot 7b, Kepler 10b. We're really starting to discover and do exoplanet physics and planetology with these systems. And of course, we were able to discover Tatooine, shown here, where we actually now have planets orbiting binary stars. And the progress just continues. I'll show here a quote that proves once again you should never say that science can never do anything. Back in 1835, Auguste Comte, a French scientist, said, "On the subject of stars, we shall never be able by any means to study their chemical composition." Well, 100 and some years later, we are actually using the Spitzer, Hubble, and ground-based telescopes to probe the atmospheric composition and vertical structure and weather patterns on planets, not just stars. We're finding evidence for water, methane, CO2, and this is just one of the spectra of one of the bright transiting systems. So this is really a remarkable step forward. We're actually really doing planetary composition. We're looking at weather patterns on the planets themselves. And I was pleased that in the choice between the two explorers now under consideration, that in fact history tells us that the planetary and astrophysics divisions jointly sat together and chose both TESS and FINESS instead of having to choose between them. And so we were able to make find a mission that did thousands of planetary transiting systems, discover those, as well as making an atlas of hundreds of ice and gas giant spectra. So I hope that has indeed come to pass. Let's see, what else do we have? The other thing that's been happening, that happened in the 2015 arena, was imaging of planets. Young Jupiter's still contracting and giving off energy from their slow gravitational collapse. We've been finding planets using extreme adaptive optics on large ground-based telescopes, presently 5 to 10 meters, eventually 30-meter telescopes. Also from space, we have Fomalhaut, we have HR 8799, and then we have Beta Pic, which first shows up on one side of the star, disappears for a couple of years, and then comes up around the other side of the star a couple of years later. So 33 years ago, from our perspective now in 2045, we have 798 planets, around 630 systems, and on top of that, another 2,300 Kepler candidates. And this just shows the discovery year and the different techniques that were being used: radio velocities, transits, microlensing, imaging, pulsar timing, and we had 0 planets before about 1989 and Dave Latham's first discovery, going back to 2000 BC when people first started speculating that there might be other planets out there. After 2015 to 2025, we have more census taking, we have images and transits from space. The Europeans are very active in this field. The Gaia mission will go up and find probably some 2,000 Jupiters orbiting stars within about 200 parsecs. The new ESA small mission, their version of small, faster, better, cheaper, called CHEOPS, just selected a few weeks ago. the ultimate in Dan Golden faster, better, cheaper mission called the James Webb Space Telescope. Went up and found water on super-Earth with spectroscopy. Also was able to image young Saturn, planets such as those that were shown here planted into an image of HR 8799 simulated with JWST. So that was a very active period. Beyond that, 2025 to 2035, we completed the understanding of planetary system architectures and imaged the first nearby Earths. We used the W1 mission and microlensing to probe out beyond the snow line. ESA's Plato mission found hundreds of Earths, for which we also were able to use astroseismology to get accurate stellar ages. NASA then selected a modest-sized 1.5-meter coronagraphic telescope and was able to image Alpha Centauri b planets C, D, and E, which turned out to exist, including an Earth in the habitable zone, and obtained spectra of dozens of other gas giant planets. And an ESA Chinese mission did the astrometry goals originally set out for the SIM mission and identified 10 habitable zone Earths among the nearby stars. Finally, in 2040, the LifeFinder mission was actually launched. It was a human robotic tended facility at L2, enabled giant telescopes to be built. There's visible coronagraph, an external occulter, a Darwin-class infrared interferometer, and announcing today at this meeting, breaking news, 3 of the 10 habitable planets found by the ESA Chinese astrometric mission proved to have signs of photosynthetic life. And now I want to enter into a little bit of speculation with my last slide. So just announcing here that complementary searches on our own solar system and towards other systems, we're able to find life in our own and other solar systems. So the Mars colonists were able to find non-DNA life by drilling deeply down into a deep aquifer on Mars. And then finally, Jill Tarter's granddaughter received the first SETI signal from one of the LifeFinder target stars. Thank you.
Oh, dear. Wasn't that a great time to be alive? I wish I could go read about it. Well, I'd like to get our panelists up to have a little bit of a round table, even though it's a rectangular table, and then we'll open it up to questions. So if we can have our panelists seated, we can try and shed some light on some of the questions that I know are still unanswered. Let's see. I guess maybe we'll go in the same order. Glenn, let me start with you. You know, one of the constants over the years has been a kind of a battle about what the justification for the science missions have been, and planetary, of course, is only one subset of that. But you know, if you and you, of course, have been pointing out that we misuse the word precursors, or we miss the nuances in the word precursors. And so I'll just throw out what may be a simplistic interpretation of the past events, which says that the planetary program is sort of like the remora that latches onto the human spaceflight shark and only makes a living as long as that shark is healthy. Has your research given you a different perspective of how planetary fits into the broader picture of the space program?
Wow, that's a big question to start with.
We don't mess around here.
No, yeah, seriously. No, I think, historians will say that there's 3 general historical justifications for spaceflight. There's the von Braun nationalistic approach, plant the flag, Gerard O'Neill's space settlement vision, and Carl Sagan belief that just understanding the solar system evokes a sense of wonder that cannot be replicated anywhere, and by studying anything else. And I think to a degree it's very possible to continue to pursue a planetary science program for those awe moments when something really spectacular is discovered. That said, it's hard to build a business case on that, and sometimes within planetary exploration that's required. And there are a lot of people who believe that settling the space system, either because of what's happening here on Earth or because ultimately humans just want to go out there and step foot on the moon, is a worthwhile goal. And I think planetary science and human will always be intertwined as long as there are people here on Earth. But definitely the urge to human settlement of the solar system is something that's very compelling, and I think we need to recognize that as a factor in understanding the course of planetary exploration.
Anybody else want to weigh in on that rather large chunk of reasoning and questioning that we've got on the table? Scott looks absolutely, you look, I can't tell if you're in a trance from that question or
I'm dazzled by the last 2 days.
you're numbed.
Yeah, no, one thing that we haven't talked about at all with respect to the planetary program is that someone observed it was an invention of NASA. Every other element has other agencies that are involved. In the earth science arena, there are many agencies that are involved. So on the one hand, that makes planetary sort of vulnerable because one agency decides if it comes or goes. On the other hand, I would argue to Jim's boss and boss's bosses that it means you have a special stewardship responsibility as well, because the return on investment as inspiration to the world is just staggering. Some people have commented on this tangentially. I know when I have a good friend who's a Spanish physicist, Juan Perez Mercader, who's started the Astrobiology Institute in Madrid. And when Mars Polar Lander and Mars Climate Orbiter disappeared, he was really shaken. He said, when NASA doesn't do well, the entire world feels bad. So I think that we somehow, through the planetary program, bring this sense of inspiration and uplift to the rest of the world.
That's certainly, I don't think anybody would argue with that, and yet we've heard so many times over the last 2 days, and particularly yesterday morning's discussions of budget, that when the going gets tough, it becomes very clear that of the space science pursuits of NASA, planetary is low man on the totem pole. And how do we grapple with that? How do we reconcile that? How do we change that? Does anybody want to weigh in on that? Is it a matter of making the case better?
Yeah.
Amy?
Yeah, I think this time around, it really wasn't so much low man on the totem pole. There wasn't any sort of prejudice associated with being prejudiced against the planetary program. I think it's a matter of timing in this case. With respect, I think we're alluding to the 21% budget cut in the FY13 budget most recently. And I think that was mostly a product of the fact that NASA and the White House and Congress have a lot of constituencies that they need to satisfy in terms of the budget, and across human spaceflight, aeronautics, space science, of course, and so there's sort of a general understanding that you've got allocations, sort of a box, if you will, and that generally speaking will go to space science, and then within space science you have the contention of planetary science, astrophysics, heliophysics, and Earth sciences and the Science Mission Directorate now as well. And I think this time around what it was there is one massive space science mission, not faster, better, cheaper, the James Webb Space Telescope, which is consuming a lot of budget, certainly, and I think that kind of mission is generally kind of scary to folks in the White House and in OMB. I can speak from that experience, and and fear to have to put in place a mission like that. You get stuck. In terms of kind of passing, running into the overruns and such. And also, there's generally a concern about leaving kind of what you leave for future administrations. Whether you buy into that logic or not is another matter, or agree with that rationale. But that kind of sense sometimes exists.
Well, let me stay with you for a second here, because one of the things that I remember, that one of my favorite anecdotes from the faster, better, cheaper era came from Tony Spear, who was the project manager on the Mars Pathfinder lander. And, they had this small, young, eager skunkworks type team at JPL that could really get in and reinvent how you land on Mars, and it was all very exciting, and of course we know how it turned out. It was wonderfully successful, but, Tony told me, here, on the one hand, you had Dan Golden out in public, boasting that he was telling his people to take risks, and that was a good thing. And in private, he was telling Tony Spear, don't you dare fail or I'll shoot you on the JPL Mall. Now, my question is, out of that, and I'm interested in your perspective also as former OMB denizen, what is the tolerance or lack of tolerance for mistakes, whether they are mistakes in costing a mission, budget, or whether they're mistakes in performance? Can you talk about what you saw from both sides of the fence?
With respect to performance, let me think about this. I think that the crowd, I mean, there are rational people. I mean, I know the decisions don't come across as rational all the time, and they're not rationally constructed.
Seems to be a lot of laughter going on in the room.
But there
Not sure what to make of that.
Yes, exactly. But there are actually people there who very much care about the space program. In fact, I mean, it may be a little known secret, but most of the folks who are at the Office of Management and Budget and at the Office of Science and Technology Policy are actually there because they believe in, if not have a background, actually, they pretty much all have a background and higher degrees in these fields. So I mean, there is a passion there, and I think there is an understanding in terms of when things don't perform, that these things happen. Usually, though, there is some sort of response, and that response is usually it's actually more money comes. When you have a performance issue, no one wants to create, or no one wants to recreate the failures of the past, and so either a mission may be reflown, as was talked about with the Orbiting Carbon Observatory. That's an Earth science example, or you see very sort of major changes with respect to Columbia, for example, and it inspiring the vision for space exploration. So I'm kind of drawing experiences that aren't necessarily solar system exploration specific, but giving you the landscape of attitude about NASA. In terms of cost, so if the missions fail in terms of cost, those are looked at, I think, really on a case-by-case basis. Sometimes the answer with respect to James Webb was to continue to fund it. I mean, but part of that was driven by consulting with the science community and also the view of Barbara Mikulski and others in the Congress. So those decisions aren't unilaterally made by OMB. I mean, the final president's budget goes out, but they're driven by the influences, I would say, of other actors too.
Scott, and this is also a question for Chaz, because both of you have described enterprises which in some ways are a leap of faith, right? Scott, the Mars program was predicated on follow the water, and you found the water, but you haven't found life yet, and there's no guarantee that even after a very careful program of reducing the technological risk of a sample return and choosing the best possible site you can, there's no guarantee that it'll be in that 2 kilograms or whatever it is that comes back. And Chaz, you've been talking about a very optimistic vision of what we might discover on exoplanets that would certainly capture the world's imagination. But what about the risk of promising something that you maybe can't deliver? Each of you would like to weigh in on that with your respective
I think the biggest challenge we have with exoplanets is the exciting goal is clearly to find life in the atmospheres of some habitable Earth-like planet. That is among the hardest technological things I can conceive of. We've laid out, you need an 8-meter telescope, well, maybe it's a 6-meter telescope, maybe it's an occulter, maybe it's this, maybe it's that. It will, whatever it is, it will be, a web-class mission to do that. And it is a hugely demanding physics experiment, first of all, and I think we've made good progress on showing we can do the physics of it, but it will be a very complicated space system that has to do that. And, one should dream impossible and great things, and we are doing it, but it's going to be a very tough experiment. And if the nearest Earth, when we finally find this parameter that I've called eta sub Earth, the fraction of stars that have an Earth-like planet in the habitable zone, is too small, so we have to look further away than alpha Cen B, for example. If we have to look to 25 parsecs, 75 light years and not 2 or 3 light years, we may not be able to accomplish that goal. It looks as though the eta sub Earth, the fraction of stars with habitable zone planets, may be as large as 5, 10, 15%. We get the statistics from Kepler, some of the radial velocity work, and so on. If they're close enough, we can do it. If not, it may simply be unattainable. And we'll just have to wait for Jill Carter's daughter to hook up to the internet.
Yeah, scientific risk and technological risk are the two things that you have to mitigate, have to understand and mitigate before you embark on an enterprise that is a decade-long series of missions, for example, with the Mars program, and the next decade that we hope comes. So let me talk a little bit about two pieces of scientific risk. One was the Viking effect, where there was an instrument that everyone believed if you took it there, reached out, because organic material was ubiquitous, you grabbed up the soil, you put it in the chemistry set, you added water, and voila, you would see the isotopes of carbon and you would have the fingerprints of life, and of course that didn't happen. So in the wake of that, what turned out to be a huge scientific risk.
Not, if I can just throw in for people that aren't familiar with the history, not only did they not find organics, the only way they could interpret the biology results was through the presence of highly reactive compounds like peroxides that would mean that the soil was actually hostile to organics.
Yes, correct. And so in the wake of this, taking this scientific risk, although they probably didn't realize it at the time, the focus of the Mars program and, in fact, astrobiology and a bunch of other disciplines moved from that hit the home run and discover life in one fell swoop to understand the habitable environment, understand the range of habitability for living systems. And of course in astrobiology that gave rise to understanding extremophiles and a range of living systems that nobody expected 15 or 20 years ago. So that was one step in mitigating the scientific risk toward finding life on Mars, is looking for habitable environments, either past or present, rather than that thing that is so difficult to do, which is to define life and create an instrument that will go and actually detect it. Second piece of scientific risk was in large part why I canceled the existing Mars sample return program in 2000. There were plenty of cost reasons. It was going to be done for $1.98 and, leaps of faith on the technologies that I showed you and so forth. But the main reason I canceled it was the scientific risk was simply too high. We had a room of this size with about 80 or 90 of the best scientists, engineers, executives in the planetary program we could find, and I said, who can tell me where to go to get a sample that is worth, I think the cost was then $3 billion, and there was no crisp answer, and the best that you got was, well, a grab sample and you'd find basalt. Well, that's not worth it. So as a result of what clearly was a major scientific risk, that was set aside, And the decade of understanding Mars as a system and looking for habitable environments came in its place. I think now we have, as a result of that effort, retired a significant amount of scientific risk. We have retired, I would say, 3 of the 4 technological risks, and as a consequence, I would argue to our friends at OMB, we are ready to do this, and it is an attainable goal.
What do you think, Amy? Has he got his elevator pitch down to a point where OMB will go for it?
It's attainable for the price, I guess, is again, the,
I
yeah,
think it is within reach.
is the.
The price is within
yeah.
reach, Scott? Okay.
Yeah, yeah.
All right. Well, at this juncture, since we've solved the problems of the world, why don't we open it up to questions? And we have the traveling microphone, and Mikhail, please.
Well, thank you. Actually, I have 2 questions, one to Scott, one to Chess. Scott, just according to the follow the water strategy you described, very wise, but it seems to me it's not completely well. Just embrace all possibilities. We are trying to look for signs of life, both extant or extinct life, just on the surface. But surface is so oxidizing environment on Mars, and possibly oxidizing go quite deep. So there are concepts similar to what we have on the Earth, deep-seated biosphere. Deep-seated, it just was discovered on the planet Earth only at the end of last century. And possibly it's even better environment for the microbes, for the primitive life on Mars. And it seems to me just it should be in the program one specific segment we specifically targeted to this idea.
Scott, can you summarize your understanding of the question before you answer it?
Yes. So this is a very good question, which is the follow the water, the last decade of Mars missions, which are characterized by this very simple phrase, have been looking for habitats that might preserve the biosignatures of extinct life. It really has not been geared toward extant life at all. So the question is, if you go down that path, isn't there a whole extra path where you might go under the surface, particularly at least 2 meters down, under where things have been gardened and irradiated, and find...
Could be a few kilometers.
Could be a few kilometers. And so this is a very tantalizing possibility. We may have evidence that periodically plugs of ice are melted and we get brine flows. It could be water is very near the surface. But drilling kilometers autonomously is a technological challenge we don't have a good answer for right now.
And in fact, it's been used as a justification for sending humans.
That's why I put that onto my last chart.
Yes.
It was the colonists who went down, Bruce Willis and the drilling guys
There you go.
were there going down because maybe that's what it takes to, or either that or you have to go into caves. You need cavers.
Yeah.
You anticipate just 25 years from now to find something similar to an exoplanet.
But I think the argument for extinct life, if you find the right types of sedimentary layers and minerals, that is the most likely strata to have preserved the extinct fingerprints of life. And that's what this whole last decade has been about.
Yeah, we really should make it clear that there are really 2 potential presents under the Christmas tree, and one is extinct life, which I think people may have hopes of, and then there's the question of existing life, which is a whole other level of investigation, and
Well, now let's wait for the methane results.
yeah.
And if possible, the second one. Chess. Again, the strategy to find as much as possible Earth-like planets and the science for life, obvious things, and different instruments and different facilities are developed. You mentioned about that. But what is kind of rationale you would propose being just in charge completely of the overall program. I mean ground-based facilities, space segment. Certainly you would say both, but it's impossible to embrace everything, you know. But we have, for example, you know, already square kilometer array to be deployed very soon. It's a powerful radio astronomy instruments in the southern hemisphere, Australia, South Africa, okay? And not saying about so powerful optical telescopes under development right now. And also we have James Webb telescope, we have Darwin and many others. So what do you think? What kind of rationale? What kind of the strategy? Because it will be very much, you know, just money-taking process. And I do not think that everyone in the community, both in planetary and astrophysical community, will enjoy it or about that.
Well, I think one of the things we learned painfully over the last decade is that whatever facilities we develop do have to be multi-purpose. So, for example, I think if we originally proposed to do an infrared interferometer, that might have been the simplest thing to go and find the infrared emission from from an Earth, sitting an astronomical unit away from his host star. That was of relatively little interest to the rest of the astrophysical community. So I think right now the astrophysics community would be very interested in a large visible light telescope that would be the next big step beyond James Webb, which of course is an infrared telescope. And that large optical telescope, optical UV, would have instruments on it capable of getting down to the 10 to the minus 10 contrast level that you would need for some observing modes, but then would also do spectra of Z of whatever, galaxies were also obtainable, so that you get a convergence of desire by a fairly broad set of people in the astronomy community. You would also have interest from the exoplanet community. Presumably the planetary community would be interested in getting spectra of giant planets, even potentially down to Earth-like planets. So I think that's the challenge, is to come up with a mission that could do that. I haven't heard a convincing argument that lets you do the spectroscopy of a habitable planet through the Earth's atmosphere. In the 30 and 40 meter telescopes that will probably be built, either in the US or in Europe over the next 10 to 15 years, the challenge of working through the Earth's atmosphere is simply too great to get you to these extreme contrast ratios that you need. And that probably requires being in space. The proponents for those telescopes argue they might be able to do it. Pretty skeptical. Of course, they'll say, gee, we're pretty skeptical that you can do it in space either, and it's a tough problem. I think space simply gives you an advantage of getting above the atmosphere that's very hard to negate. So I think that's where we're going to go, and it may take 20, 25 years to get there. I put it in 2040. Maybe I was being pessimistic. Maybe I was being optimistic. We'll have to see. But it will be challenging technologically, and that's because the physics dictates what you have to do. If alpha cent B, planets C, D, and E are in the habitable zone, that helps enormously. Then you're talking nearly an order of magnitude simplification in the problem, just because the planet is that much further away from its host star, and that's what drives the difficulty.
Okay.
This question is probably for Amy, but I'm sure Scott and Chaz and others will have an opinion on it as well. We've talked a lot over the last few days about ebb and flow of budget, ebb and flow of the pace of missions, and ebb and flow of success. But we haven't talked about one of the factors that could be a contributor, and that is recognized in some other areas as a contributing factor, and that is the training of the continuity and training of the workforce. In the lost decade, we had many less engineers working on planetary spacecraft and developing the systems. And did that contribute to what we did achieve and didn't achieve in the 1990s? And in fact, is the success, the remarkable success of the last decade, in part traceable to the success of being able to consistently hand off the responsibilities for development, engineering, and operations from one well-trained group to the next well-trained group? Your thought? It's a topic we haven't talked about at all in the last 2 days.
Talked about, and I have no idea in terms of tracing, you know, the particular strains that you're talking about and the relations.
Okay, but Chaz and Scott both think it's critical.
Yeah, I would defer to these.
So let me give you one real clear-cut example. When I was in Pasadena before we gathered at JPL for the Curiosity landing, I was down at the Planet Fest event, and I ran into Rob Manning, of course, the chief engineer for Mars Science Lab Curiosity, and I've known Rob since 1993 or so. And I said, "So, Rob, how's it going?" He said, "Enjoy the show. It's going to work." Now, I realized that, you know, he was pumped up about the whole thing, but I said, "So, you know, why?" He said, "Look, we have tested this thing. We had years and years of testing. We've tested overlapping things in the case that we can't get the exact environmental condition. We've done every conceivable failure mode and so forth." And he said, "We're highly confident this will work." To that explanation, I will add that Rob Manning and Cookie and the others started with Tony Spear on Pathfinder in 1993. They went through Pathfinder, they went through Spirit, Opportunity, Phoenix. This was their 5th landing on Mars, and you have a cadre of people who have learned all those tools and techniques. And the numbers I showed you to do the caching rover, that one of the reasons that you can say that's a good number and is so low is because you're counting on those people being there.
Exactly.
If you delay this, and this is what I tell to my OMB OSTP people, they don't believe it, but if you delay this by 5 to 10 years, these folks have to make a living. They'll go somewhere else. You won't have this expertise.
It's something that we understand in human space flight, and it's been talked about a lot. It's been talked about a lot in the launch vehicle development community, where that was lost and is now being rebuilt, and it bears here as well on planetary.
It's true in astrophysics. It's true, you know,
Yeah.
at JPL in all different areas. You know, as
Well-
these giant missions suck up all the oxygen, you lose people in other parts of the program, and it's very discouraging to have somebody land on Curiosity and say, "Well, gee, I need a charge number starting next week because I just finished EDL. I wonder where else I can go." And they'll go somewhere, and you lose the best people first.
Well, in fact, it was part of the justification for the NASA Lunar Science Institute was that we had not done any lunar science in quite some time, and we needed to train a whole new cadre of lunar scientists.
That seems to be working very well. And, you know, I think one thing that came very clear in this conference is the enormous perspective that some of the people who have been in the space science community for so long bring to it. I mean, they're not just building spacecraft, they're building instruments, they're fighting budget battles, they're developing planetary models, they're archiving the data, they're training people to follow after them. And it's just been remarkable to hear from some of the people who have been involved for so long about what sort of experience they have gained.
Okay, Greg?
This dialogue is a perfect intro to the question that I wanted to put to Amy, which was why I stood up. And it's not to put you on the spot, but you did comment that the folks at OMB and upper reaches of NASA who made this decision concerning the fiscal 13 budget are smart people, intelligent, well-educated, and of course we know that to be the case because we know them ourselves. The question that I have for you has 2 parts. Do they understand the implications of standing down for 5 or 6 years and the loss of this workforce? And if so, what does that tell us about their true intentions? If they don't understand, the implications of standing down for 5 or 6 years, why not? And what can we do to help them understand this? And again, not to put
Not
you
to
on
put
the
me on
spot,
the
because
spot,
you
not
weren't
to put
there
me on the
and you
spot.
didn't do all
Thanks
that.
for-
No pressure at all, Amy.
caveating that. Yes, I mean, so to answer the yes/no part of it, yes, they do understand the implications of standing down. And it's a real problem. I mean, and, you know, I think everybody there would like to see, you know, everybody, you know, at OMB, oh, I shouldn't say everybody, but, no, I hate to you know, but on the whole, I mean, again, the folks there who are reviewing the NASA budgets are supporters and you know, want to see NASA succeed and do great things, as do so many people. That, you know, the challenge is faced, though, that there is so much content there, and choices have to be made. There's a lot of instances where, you know, there's issues of these standing down, and if we stand down, then we're not going to be able to do X and Y. And at a certain point, you can be propping up armies, if you will, and I don't mean to say, I mean, it doesn't sound, you know, totally diplomatic to say that, but just, and keeping folks going for the sake of preserving a capability that you're going to use in 10 years. I mean, we could say that across, you know, various disciplines, and if we're constantly doing that, you know, the question is where's the budget for the content? I don't have an easy solution. Obviously, the people there don't either. And I mean, I would love to you know, have more dialogue, you know, with the community about, you know, what solutions might be possible to mitigate this. Is there a way to cross-train people? And I mean, and some of this goes back to, you know, prior to people enrolling in the workforce, but is there a way, I mean, as you're, you know, in school and you're in an engineering field, and you know, that you become cross-disciplinary and that you're kind of prepared for these sorts of shifts and changes to have to occur. And then there's the question of how you preserve the institutional knowledge. I mean, that is a big one. But I mean, these are two things I think we have to conquer, and not just see budget and carrying of people as the solution, but as, I mean, that there are other things we might do to preserve the.
Well, it kind of comes down to basic economics. The people who made it possible to make the progress that Scott showed on one of his charts. He picked one example of the landing aerolifts and how that has shrunk over generations. Has taken a constant effort on the part of now 2 generations, and none of these people studied how to do that in school. There's no field for that. And it's such a niche area that there never will be a field for that unless there's a job out there for them to go to.
It's so
So
specialized.
if you don't, it is so specialized, and yet it is absolutely enabling, just like the deep space navigators who navigate the Cassini spacecraft. Every single day, they are changing the trajectory in order to be able to do those flybys. That's the only market for what they do. So if indeed the folks over at OMB do understand that this means losing that, that's tantamount to saying that they have decided that it's okay to cede this area.
Okay, I'm not sure we're going to solve this one.
But it is, I mean, it's a zero-sum game, so it's
Yeah.
a choice. It's a
Okay.
choice. Everyone's
Thanks.
choice. Yeah.
Janet?
Thanks so much for a great panel. One of the things that struck me that cuts across all the talks is a particular thing that is very powerful, and more powerful, I think, than RTGs, and more powerful perhaps than OMB, and that's the power of talk, or specifically what academics would call discourse, and that is particular kinds of ways of talking that are shared by different members of different communities. And I'm thinking of several of these because they're important, especially in Amy's paper, which was brilliant, articulates exactly how that talk works in a network. So things like faster, better, cheaper, or follow the water. These are things that we all know. They're common ways of talking. They're discourse, right? But they're really powerful and important because they pull together actors in that network in a particular kind of way, and they justify activity in that network. They're also important because you can have anticipatory talk. You can have future discourse, right? Whether it's the discourse of the Precursor mission, or, as I would argue, the discourse of Mars sample return, right? These are particular things that haven't happened yet, but we're talking about them in a particular kind of way to pull those people into some kind of alignment. And thirdly, I think it's important to pick up on something that Glenn mentioned at the beginning of his paper, which is that the ways in who gets to tell the stories actually betrays a particular kind of politics, right? That, you know, that JPL is such a strong actor and not necessarily Ames or Johns Hopkins, et cetera, right? And that's the result of kinds of ways of talking in the network. And I want to take advantage of the fact that we have both historians and practitioners in this room to actually have a conversation about what it means to talk this way. Because I think for historians, it's really important for us to not take that discourse as the explanation, but as the thing that needs to be explained. And I'm very curious as to how we might do that. I think the Sociotechnical network is a great way of getting at that, but I'd be very curious to hear about that from your perspective. And then for many of the actors in this room who've played such an important role in pulling these missions together, in formulating phrases that have been so meaningful and powerful, what is your role, do you think, in putting these phrases together and mobilizing the network? What does it take to get those words to travel? And not just travel to Washington, but travel to Mars and to Saturn. So I'd love to just open up to the panel an opportunity to talk about what discourse means, what it means to talk, where these different kinds of phrases and expressions come from, and how and where they move, and what gives them the power.
Anybody want to take a shot at that?
You know, Kurt Vonnegut said, any physicist who can't explain what he's doing to a 9-year-old is a fraud. So you have to be able to intellectualize what you're doing, why you're doing it, and explain it to a broad range of people. 9-year-olds, congresspeople, administrators, peer scientists. I mean, you have to... no comment. I mean, you have to be able to have a discussion at a very high level with a cosmologist whose mission you may be saying, well, gee, I want to delay your mission by a decade so that I can do my exoplanet, or, you know, explain to a congressperson that there is a reason why it's interesting to go find life on some, you know, planet that's hundreds of light years away, and have them say, yeah, that's a good thing to spend money on, even if it's not going to put a bridge in my district.
I call it haiku for science. You need to explain what you're doing in 17 syllables. And that was the power of Follow the Water. And if somebody wanted to know more, you could go on for hours. If they were satisfied with a simple explanation that is literally the elevator pitch, then that's fine too. Words have immense power. And one of my quibbles with the characterization of Mars sample return is that is a technique. The real goal is understanding habitability and present or past life on Mars. It just so happens this technique is the one that the community agrees is the most powerful technique for making a huge step in understanding. And what's occurred is that the technique has been characterized as the end goal. The end goal is understanding the presence or absence of life on Mars.
Okay, I think we've got time for one more.
What's the role of new up-and-coming participants? China, maybe India, Brazil, where do they fit into everything that's going on?
Well, let me just start sort of in response to Janet's question as well. Where they fit in terms of understanding space policy is they're a different group with different motivations, different social technical networks like Amy was talking about. We spent a lot of time talking about NASA administrators, Congress, what is involved in making them understand the goals of space science, and in different communities there's different ways of talking. Part of the reason we do history is so that we can look at, you know, stepping into the same river at different times. Space science looked different in the 1960s than it did in the 1990s. Part of the role that historians play in a conference like this in talking to policymakers, there is this goal to simplify and focus on terms: Mars sample return, faster, better, cheaper, precursor, exoplanet exploration. But historians have an obligation to sort of go back and unpack what those words actually meant and how they actually were implemented. I mean, Mike Neufeld gave a very interesting, in some ways very chaotic, paper about the explanation of the invention of faster, better, cheaper, and how it really happened. Eric Conway likewise gave a very interesting paper about the image of Mars sample return, suggesting that in these periods where some people can look back and you know, see a path from where we were to the present, and people working in those era could have come up with a very simple explanation for how things happened. There actually was a fair amount of contest, a lot of people with different missions trying to figure out which way to go. And I think we also need to understand, that NASA, it's not, we live in an age over the past 50 years when NASA has been the big player. There are missions like exoplanet exploration, Mars sample return, that no other type of organization can do. But NASA works within a much larger context that includes the international partners, universities, commercial firms that work on subcontract or commercial firms that have other commercial aspirations. And yes, figuring out how all these different people can talk is one thing that I found most valuable about this conference. But that's not a direct response to your question about the international partners. Maybe there's another.
New international partners, say the Chinese, are slowly becoming integrated into the astronomical community, first in the ground-based. They'll probably be a participant in one of these large ground-based telescopes. The TMT project is likely to have Chinese participation, maybe also Indian participation. I think as you build up the interpersonal and scientific collaborations, assuming the politics works out favorably over the next 10 to 20 years, you may well have China being as well integrated into what we're doing as we now have with the Europeans. Could not go that way, but certainly there's talk among astronomers that, China would be an obvious place to find support for our ground-based aspirations in 10 or 20 years, maybe for the space-based ones as well. They certainly have an active space program. It's not yet integrated into the NASA or European world yet, anti-integrated, but that can change.
Let me ask Scott, we saw on Mikhail's slides, I'm sure you noticed, and I don't know what your reaction was, and you probably knew this, the Russians are planning a Mars sample return mission for about the same time period that we would be. And having grown up at a time when many people were asking, why are we competing with the Russians and going to the moon, why aren't we cooperating? And of course, we've seen many iterations of that. At this point, does it make sense to talk about a joint sample return mission and spread out the risk, spread out the cost?
Well, the ExoMars collaboration was intended to be the first step toward a NASA-ESA collaboration on sample return for exactly the reasons you mentioned, which was to spread out the cost and diffuse the risk. Right now, the international collaboration in that particular arena is low for a variety of reasons. I think it will come back. I think certainly the human exploration of deep space is going to be an international endeavor. In somewhat direct response to your question, you can ask the question, why explore space? And there's an hour lecture I give that has the 6 reasons I've collected. But the first of those for nation states is that it's a significant badge of accomplishment. There's only the Soviet Union and the United States that have had the independent ability to put humans into even low Earth orbit. The Chinese are following the Gemini Apollo playbook, and it is for them a badge of accomplishment, and as far as I can tell, it is for India as well. There are many, many applications of Earth orbiting spacecraft for disaster relief and so forth, but where you ask the question of, why put people in space, you cannot ignore the national interest part. And I think that's what drives some nation states to want to do that in the first place.
Okay, Torrance, you want to make a point?
I just wanted to make a very brief pitch for optimism. In the context of the time that all of this takes. 1610, Galileo discovered the solar system effectively. By 1710, Isaac Newton had it figured out how it worked. we're still ringing changes on the restricted three-body problems with all of these trajectories we're talking about. We're talking about a field that's half that length of time long. And my own terms, I've been working on Cassini one way or the other for half the time since the launch of Explorer 1. Now, it may mean I'm old, but it also means this field is young. And during that time, we've gone from 0 exoplanets to over 800, and I suspect that Chaz's future history is actually conservative.
I can't think of a better note on which to end our panel. Thank you, Torrance, and thanks to everybody on the panel and to the audience.
Well, gentlemen and ladies, it's time to close our symposium. I would like to think that we have learned a great deal during our 2 days here. I will point to two things that I think are very valuable for us as we think about this particular conference and as we go forward. The first one is the interplay of historians and other social scientists with engineers, program managers, scientists, I think has been a very rewarding experience and quite synergistic. And so I hope that we take that away as something to pursue in the future when we think about these sorts of issues. Secondly, one of the things that we have learned through the 2 days is how much we don't know. There has been more questions raised than there have been answers offered. And that's to the good as well. The history of planetary science, of solar system exploration, is a very rich one, and I hope that we will continue to pursue it into the future. I know the historians we're going to mobilize to try to do so, and we're going to be calling upon all of you who are practitioners to help us. As we close, the first thing I would like to do is just to acknowledge our sponsors, NASA, JPL, the Smithsonian, Lockheed Martin, for all of your excellent support for the activities that we've done for the last 2 days. So could we have a round of applause? And could we also have a round of applause for all of the presenters and all of the people that made this possible? All right, with that, I will gavel. I declare our sessions closed.